Welcome to the student presentation part of GEOS 5375 Tectonics. We're looking forward to your presentations. Thank you for sending them in. So just to remind you and the international audience of what we're going to put online, because I didn't get any emails from anybody saying they would prefer not to, so we're going to do that. So this is old news for you, but new news maybe for some people watching for this. So the oral presentations are a talk with 9 slides maximum given on some problem in tectonics. You've identified a problem in tectonics that you find interesting, and we've discussed your possibilities, and you submitted a few sentence written proposal on March 5th. And then today you're going to give your talk to the class as a PowerPoint. Clint has all of those PowerPoints, and all you have to do is say next when it's time for you to move to the next slide. So each presentation must consist of a total of exactly 9 PowerPoint slides, including 1 title slide, right, and 1 reference slide. So, and then there is a location slide created in GeoMap app. And you all know about GeoMap app because I forced you to learn about it. And the other 6 slides are made by you. So they, as you know, they do not need to be computer generated. They can be sketched or traced, but they must be generated by each student. And I will subtract points if any figures are not made by you. And the total presentation can take no more than 10 minutes plus 5 minutes for questions, which should get us through the class.
Hi, good morning, everyone. My name is Chaturi Vadsundara, and today I will be presenting on crustal deformation and mountain building in continent-continent collisions. This topic is crucial in understanding how major topographic features like mountain ranges are formed through the tectonic processes. So, Earth's surface is constantly changing, as we know, due to tectonic forces. So one of the most dramatic examples of this is collision between continental plates, which rehabs the topography and builds mountains. A key case is this presentation formation of the Himalayas due to the India-Eurasia collision. Understanding these processes is vital for interpreting Earth's history and especially for anticipating geohazards. In this presentation, I aim to cover 5 main objectives. First, explore how crust deforms during continental collisions. Second, understand how deep Earth process influences surface topography. Third, use real-world case studies to ground these concepts. Fourth, evaluate how current data and models are improving tectonic theories. Finally, assess the implications for hazard predictions and mitigations. So in this slide, plate convergence and crustal deformation have been discussed. So when 2 continental plates collide, neither easily subducts due to their buoyancy. So instead, this crust thickens and shortens. So here you can see the pictures, images that I flashed. So forming fault mountains happens. So this convergence generates intense impressive forces causing uplift and the development of thrust faults. These effects can extend over thousands of kilometers, so showcasing the scale of tectonic deformation. So now let's move below the surface and examine what's happening deep in the crust and lithosphere during continent-continent collisions. So these processes are often hidden from view but are essential to understanding in maintaining mountain building. So here the diagrams have been shown to you in crustal thickening. As plates collide, you can see the crust doesn't just compresses at the surfaces, so it also thickens vertically. So in the lower crustal floor, at, at great depths and under high heat, the lower crust can behave more like a viscous fluid. So in the lithospheric flexure, the lithosphere can be bent under weight, a process known as flexure. So this can create foreland and basins and or uplift areas adjacent to mountains. So and the role of temperature and the composition also matter a thing. Forming of mountains. So temperature and the rock type strongly affect how the crust and lithosphere deform. So and then the final part is the delamination. So in some cases, the dense lower lithosphere detaches and sinks into the mantle, a process called delamination. So this can trigger surface uplift and volcanic activity. So in slide 6, in my case studies has been mentioned. So the target case study is Tiban Plateau. So Tiban Plateau is the prime example of continental collision dynamics. It is the largest and highest plateau in the Earth, I would say. So formed by the ongoing India-Eurasia collision. Some areas shows crustal thicknesses exceeding 70 kilometers. So features like active faults and GPS tracked uplift patterns suggest complex interactions between surface and deep process. So, investigative methods and tools. When we talk about the investigative methods and tools to study these deep processes, we rely on a range of geophysical tools. So, seismic tomography reveals substances and structures, and GPS geodesy measures surface motion, and remote sensing gives us elevation and deformation data. So, numerical models help simulate stress and strain and temperature changes over geologic time. Unresolved questions in this slide 8. So, despite these tools, many challenges remain. So, deep crustal regions are hard to access, and their composition and viscosity are not well understood. So these are still a debate over whether lower crustal flow or brittle floating or partial melting dominate. So moreover, tectonic responses vary along different mountain belts. So making it hard to generalize. So linking short-term observation with long-term geologic trends is also a difficult. So let's come to the last one and the broad significance and the conclusion. So studying crustal deformation is not just academic, it improves our models for earthquakes and landslides, helping protect lives and infrastructure. So it also helps interrupt in the ancient mountains belts and access the interplay between climate and tectonics. So overall, it enhances our understanding of how continents evolve through geologic time. So that is the end of my presentation. Thank you so much.
So I will ask one then. Can you go back to your tomography slide? Okay. This image does not really look like a tomographic image or a magnetotelluric or a GPS or can you explain why you chose this particular image for the investigative methods and tools?
Oh, actually, this has automatically selected with the PowerPoint, so I'm sorry for that.
Oh, you did not generate this.
Yeah, this not does not generate it.
Okay,
So I
well,
have,
that's
yeah.
unfortunate, but The rest of your figures, clearly you spent a lot of time generating them,
Yeah.
but
So
but
this has, yeah.
but overall, it's a very difficult topic, as I'm sure you appreciate. And I think you did an excellent job summarizing why we are interested in this topic. So thank you very much.
You're welcome.
And let's go on to talk number 2.
Good morning, everyone. So, as part of the requirements for this course, I decided to look into the role of magmatic process in continental extension. So I used East African Rift System as my case study. So for my introduction, we know that we're all sitting on continental plates, and each of these plates, and these plates moves every now and then. So, and when these plates move towards each other, we have a convergent plate. Just like example is the Himalayas, what we have there. Then when these plates move relative to each other, we have transform plates, just like we have in Sahandra's fault. Now, when these plates move away from each other, then we have divergent plates, which gives rise to rifts. And an example of it is the East African Rift System. So for my presentation today, I have some introduction outlined and also learning objectives. So first, one might ask, what is continental rift? So continental rift is actually a thinning process of the lithosphere, which can be visible on the surface, which leads to rupture of the continent, thereby separating the continental crust and giving rise to new ocean. And East African Rift System is an active rift, which is example of this kind of divergent plate boundaries. And it extends over 3,000 kilometers, ranging from Ethiopia, passes Tanzania, Kenya, down to Mozambique. So for the learning objective, what I expect us to get from this presentation today is first, that we need to understand that continental rifts is a tectonic process. And in East African Rift System, we have, we have different kinds of rifts. We have the Eastern rifts, we have the Western rifts, which I'm going to talk about shortly. Then we also need to evaluate the mantle plumes, that is causing this rift in the East Africa, and also investigate the relationship between the magmatism and the continental rifting process. So I generated this map with GeoMap app, trying to explain what is going on here. So if you look at what I'm looking at, it's a map of Africa. So I'll try as much as possible to explain it so that some of our viewers who are not tectonics experience can have a glimpse of what I'm talking about. So here, if you look towards where I have the ET means Ethiopia, down to where I have TZ, which is Tanzania, there is an active rift going on there. Although the rift have not fully developed, it's still actively going on. That is why we're not able to see something. You see where I have a Gulf of Eden. So that is a rift that has happened in the past, separating the Ethiopian rift and the Arabian plate. Now, this rift is happening on African plates. So whereby on the right, we have Somalian plates, and on the left, which is on the eastern part, on the western part, sorry, we have the Nubian plates, and I'm going to explain it further in the next slide so you can understand what I'm talking about. Now, the arrow I have is just to show that this continent is pulling apart from each other. So with time, we're going to have something similar to where I wrote the Red Sea, giving rise to new ocean coming up. Okay, yeah. So let's talk about the geologic setting of the East African rift systems. So looking at the diagram I have on the right, now we see the western branch of the rift. Now the western branch of the rift lies on the Nubian plates. Originally, these plates are all African plates, but because it's rifting apart due to the magmatism, they are beginning to have different plates. So on the left, we have Nubian plates. On the right, we have Somali plates. Then if we look towards the light blue, you will see Ethiopian rift. Then coming down, you will see another eastern branch of the rift. So what this is telling us is the rifting process is happening in phases, so to say. We have the western branch that is rifting, and we also have the eastern branch that is also rifting. So, but all of this rifting is happening on the same plate, which is the African plate originally, before this rifting started. Now we're having Somali plate and Nubian plates due to this rifting. And it's also important to know that this rifting process began about 25 to 30 million years ago. So it's not something that happened today. And who knows, it's still going to take a couple million years for this rift to be actively completed. And yeah, it's also characterized by extensive volcanism and faulting. So what this means is this rift actually starts due to the mantle movement from the asthenosphere as it's moving towards. So this is a cartoon picture I tried to create to show an active volcano that is ongoing right now in Tanzania. It's called the Oldonyingo Lingai, something like that. I'm not sure if I got the pronunciation properly. So yeah, for the magmatic process, it's important to know that it's basaltic magmatism dominates the volcanic activity, and as the magma intrudes the lithosphere, it weakens the continental lithosphere, giving rise to faulting and rifting. Then it's also important to know that the thermal effects promotes crustal thinning, whereby we have the thinning on the surface, just like we did in our course, where we have crustal thinning. I can't remember the chapter in our course. So I decided to talk about the structural architecture. So it's important to know that the rift is characterized by normal faults. So what this means is that we have transform faults, we have normal faults, and other types of faults. So what this means is that as the surface is stretching, it's forming a linear valley, like one is higher than the other, showing that rifting system that I would see. Just that we're not allowed to use live pictures. I would have been able to show what is going on there actively as we're talking. And we also need to know that the magma tectonic interactions, influences the crustal rheology. So what this means is that as the magma, intrudes the surface, it kind of determines the way the lithosphere reacts, leading to faults. That is the way it reacts to stress and strain, which could cause faults. So this is as a result of the magmatic heating as the asthenosphere is making its way to the surface. And it's also important to know that the magmatic underplating modifies, the crustal structure. So yeah, I try to, create a 3D picture of how this looks like. So if you look at by both arrow, this is just like a representation of the lithosphere, so to say, as it's pulling away from, as the plates are pulling away from each other, it's creating this gap, like if a fault line, that's giving rise to the creation of the new ocean. So some of the implications of continental rifting is volcanism. Definitely has to be volcanism before this, plates can diverge apart. It causes earthquake, just like we have in Tanzania, some in Mozambique as of today, and also lithospheric thinning, just like I explained earlier. So for conclusions, we need to know that East African Rift System demonstrates the critical role of magmatism in rifting, and the magmatic process facilitates continental extension as the magma is making its way to the surface. We're having crustal extension on the surface. Thereby, when you get there, looking at it on maybe a remote sensing map, you will see the crustal thinning ranging from Tanzania all the way to Mozambique, and it's as a result of the magma. And it's also an important implication for understanding rift evolution, how the rifts, came into play, what are the active roles that contributes to this rifting, and it's a very good example to study continental rifting and active continental rifting. Yeah, so these are my reference according to the Geophysical Journal Standard. Thank you.
Very good. Do we have any questions?
Actually, I do.
Okay.
I guess I'm not sure as I understand the whole volcanism over there. I mean, you got, I think that one volcano that erupts constantly in Ethiopia, and then you got, Kilimanjaro, but it hasn't erupted in a long time. And I don't think there's any active or any volcanoes to the south. And I'm just not sure, is that right? And why is that?
There is. The Aldo Lingai volcanism is an active volcanism as of today in Tanzania.
Well, it's an excellent question. And part of it has to do, you mentioned the fact that extension is larger in the north than it is in the south, which brings up the way you've depicted the Ethiopian rift relative to the eastern branch.
Mm-hmm.
The Ethiopian rift is simply the northern part of the eastern branch. It is a very different kind of igneous activity than farther south where the extension is lower. And by the way, the Ethiopian rift and the eastern branch goes out to sea at Djibouti. Djibouti is a very small country, and that little bay there is basically where the extension center goes out into join up with the Gulf of Aden.
Okay.
And also the rift continues north into Eritrea, where there are some very active volcanoes. Erta Ale is one. But if this was a class in petrology, we would be emphasizing the difference in the composition of the igneous rocks that are produced along here. As you can imagine, they vary a lot because the extension is much greater in the north than it is in the south, which means the asthenosphere, which is the source of all of these basaltic magmas, is much closer to the surface, and therefore it melts more in the north than it does in the south. And by the way, Oldoña Lengai is of great interest to petrologists because it's the only active carbonate volcano on the planet.
That's true.
And so that is of particular interest to petrologists.
What do you mean by carbonate volcano? It's magma just coming through an old carbonate formation?
No, it's magma is sodium carbonate.
Oh.
Instead of, all magmas are basically silicate
Yeah.
melts, except for Oldoña Lengai, which is a carbonate magma.
Where is that? Is that in Ethiopia or is that in Eritrea?
It's in Tanzania. So that brings me to the question, because when I was trying to put up the slides, I couldn't help but think, why is that particular volcano having carbonate materials as compared to other ones, and is the only one in the world that has carbonate, while other has siliclastic. So is there a reason for that, Prof?
Well, number one, carbonate igneous rocks are not, they're unusual, but they're not, it's not unique. What's unique about Oldoña Lingai is it's an active one. So if you go to Arkansas, there are places where you can visit in, Cretaceous intrusive carbonate igneous rocks. The original ideas were that these were melted sedimentary carbonates, which was demonstrated to not be the case through looking at isotopes. And since that time, what the petrologic community agrees on is that these kinds of unusual magmas reflect low degrees of melting of unusually enriched parts of the lithosphere in particular. And that, in general is the explanation. There's a lot of carbon and carbonate in the mantle, and it has accumulated underneath Africa because Africa was part of a supercontinent. You had this huge lithospheric cap that captures all kinds of things slowly diffusing up from deeper in the earth, and it's being tapped now. That's my 5-cent explanation. But I think it's time to move on. Thank you for a very interesting presentation. We've had a couple of really good talks explaining major features of Earth's tectonics. So let's hear the next one.
Mine was, Professor suggested I take a look at the Cascadia convergent margin, which is really kind of the Juan de Fuca plate. And it's a fascinating area. And why? Mainly because of it'll probably be the source of a very large earthquake and maybe the U.S.'s first large tsunami. When, hopefully not in my lifetime, but young kids may get to see it. So here's the plate. It's outlined in black there. It's about 200, small plate. It's about oceanic plate, about 250,000 square kilometers, about 1/400th of the side of the Pacific plate to the west, and about 300th the size of the North American plate to the west. It's part of the old Farallon plate that subducted underneath California, and it's been subducting for the last 40 million years. It won't last that long. It's one of the most intensively researched places on the planet, I think. I don't know that for a fact, but I saw 4 big oceanic surveys, seismic surveys, and just looking briefly through it. The plate's moving northeast as the North American plate's moving north and west, subducting at a slow rate, 30 to 40 millimeters per year. It's a young plate out there. And it's a little, such a small plate and such a young plate, it's obviously a warm plate, but it's a little bit different than, say, the Andes, where there's very no sedimentation. Here you do have a lot of sedimentation, which comes off among other places, the Columbia River. It's also a great story is because it's kind of interesting because of sciences and scientists working together. And we really didn't know this is not a very active plate. There's very little seismic activity, or at least on the plate itself. And it was some work by some scientists on the West Coast that realized, going out, and you can see my bad picture down the bottom, by looking at dead wood and grasses, and then seeing the normal Pacific Northwest nature behind it out there. And they realized there had been a tsunami there, an earthquake and a tsunami. You had significant subsidence too at the time, anywhere from tens of centimeters up to 2 meters, depending on where you were on the coast. And when it first came out, they just looked at carbon-14, and all they could do is, they really weren't sure, but they thought somewhere between the early 1600s and maybe as late as 1800, this earthquake and tsunami had happened, and published on that. And then there was a professor in Japan that basically knew about an unknown, a tsunami of unknown origin that took place in Japan. And they've tracked their tsunamis for a long time, but they didn't have an earthquake to go with it. And he was basically proposed kind of a magnitude 9 earthquake coming off here that hit Japan, that At Japan, the tsunami had wave ramps of between 1 meter and 5 meters in various places out there. And then, frankly, there was some great detailed work on trees and spruces, and they could go back to a lot of these trees, and they literally could pin them down to they died in 1699. So they knew the earthquake. This had basically been the funding of the source of this January 26, 1700 tsunami in Japan. What do we know? As I said, this is a young plate out there. It's all less than 15 million years in age, so it's obviously very hot and buoyant, and it's a difficult subduction. The interesting thing, if you look at the seismic activity, is it's really split into three plates. There's the Explorer plate to the north, the Gorda plate to the south down there, and then the Juan de Fuca plate. But what you see is almost all the seismic activity, and this is since 1960, has been strike-slip action on the southern end of the plate and other deformants out there. And so, you know, back in the mid 80s is kind of a question of why so little activity. Is this, you know, an aseismic thing and the plate's subducting fine out there, or is it totally locked and it's going to be the next source of a next huge earthquake and tsunami probably? The last thing that makes it interesting to me is if you look down at the bottom, my little red dots and stuff, but it shows kind of the seismic activity by longitude, 40 degrees being California to the south and 48 degrees being the border and Canada, US, Washington to the north. And it's interesting because you see a lot more activity in Washington and California, a lot less in Oregon. That's probably due to a thickened igneous section they have out there, which I won't go into anymore. But so what's presently going on? And really, this Heinemann came up with the theory that it was locked, and based on just going thermodynamically model, and it's proven out probably. First version was in 2013, and it's amazing his maps today. 12 years later, we got much better data, but they're still holding up fantastic. And what he saw was basically once the plate got to 150 degrees, it would probably lock, is because the water-bearing clays, which is smectite, would move to illite, which would not move on the plate. And then it would stay locked essentially till it got to a depth and temperature of 350 degrees Celsius, which is where you go through the brittle ductile transition, down to about 450 when you know for sure it's traveling smoothly. And this is a bad graph over there, but you can kind of see what's going on. So we do have this plate that's basically been locked in place and accumulating a lot of stress and strain up to, I've seen numbers up to 14, 15 meters on it since the last 1700 earthquake out there. The one thing that you do see a lot of activity, especially on shore, is called this episodic tremor and slip section, which is basically what happens is the water's, because there's a lot of cementation, there's a lot of water going down until it forces a serpentation. And then at that point, it's forced back up and it causes all these episodic tremors and slip on the onshore part of the segment. And you can kind of see up at the top, you can kind of see where this is all happening compared to the big cities, Seattle, Portland, Vancouver, and then the volcanic arc to the east of those cities out there. So I guess then the question is, how often does this happen? And there's been lots of studies out there. I think Atwater and Hemphill were one of the first ones out there. There are some other ones who were looking at basically deposits off Vancouver Island. You can't go back too far off Vancouver Island. You can only get depths of about 1,000 years old out there. But they were seeing one of the bigger ones they did had covered 3,500 year time period, and there was 7 big tsunami deposits out there. Clegg did some, Nelson did some, and anyhow, then Goldfinger did something different. He started looking at the turbidite deposits offshore. But the interesting thing is all these people come up with the time period is anywhere from 200, but on average about 500 years. between these tsunamis we see that hit the West Coast. So anyhow, we obviously have accumulated a lot of slip on this thing, or a lot of, not slip, accumulated a large enough tension, stress on the plate that it can and will probably do a large earthquake out there. Almost all the scientists that look at this, I don't really look at the data and know enough to criticize it or whether it's legitimate, say that it will rupture the whole plate out there. And when it does, that's going to be a magnitude 8, magnitude 9 earthquake. I see tsunami estimates of anywhere between 80 and 100 feet. Now, I know nothing about tsunami modeling, but taking it right, it'll be a significant disaster. I'm not sure it's going to be as bad as the New Yorker magazine that said everything operating west of Interstate 5 will be toast, 30,000 landslides in Seattle alone. You'll have damage as far as south as Sacramento, and it'll be months to years before things will be able to be restored. But certainly this is something that needs to be watched. It could be a significant disaster out there. I tend to think the big cities are protected. I mean, Vancouver's got Vancouver Island between it. Seattle's got, a lot of land between itself and the coast, and Portland's inland by quite a ways out there. But and then my only questions really on this is how good are tsunamis that we see, these deposits, turbidite deposits or onshore deposits. Are those really mean that they were coming from the Juan de Fuca plate? They could be coming from anywhere. I mean, 64 Alaska, the big quake there had tsunami deposits down here. The 1906 San Andreas, San Francisco one had tsunami deposits down there. I mean, I was looking at some data that showed you could see tsunami deposits from Chile earthquakes, Indonesian earthquakes, all over the Pacific on the coast. So are we kind of overcounting every time they see a tsunami deposit? Does that mean that it came from the just the Juan de Fuca plate out there? And then my other question would be, turbidite deposits, do we know the fact that they've been caused by earthquakes? I mean, I see lots of turbidite deposits in the Gulf of Mexico, and I'm not sure anyone was caused by an earthquake out there. And there's some interesting things. I mean, the Juan de Fuca submarine channel alone carries more water than the Amazon River does. So, I mean, that I would think might set up a lot of turbidite deposits and stuff like that. So, but it's certainly an interesting area to look at and research, and something to watch for the future. So with that, I will stop.
References, please. All right, questions.
There's 2.
Anybody got any questions? Well, and I'll ask one. Can we go back to your cross-section sketch?
Yep.
And I know this is challenging to draw because we just don't have the definition of the Wadati-Benioff zone that we have for other convergent margins because of the lack of seismicity. It's these deep earthquakes that really tell us what the subducted slab looks like, the subducted Juan de Fuca plate looks like, and we don't have that. So it has to be worked out from tomography and other things like that. And I think you've done a pretty good job here. Now, one of the things you talk about is Heineman's model. Heinemann, our dean is also named Heinemann, and this Heinemann, Roy Heinemann, who recently passed away, was his uncle. Interesting story. It's a family of geoscientists. Now you talk on the left. You show the locked zone, right?
Yeah, it's a bad drawing, but the pink part.
No, and I'm not accepting apologies. Okay. But what I want is, where would the lock zone be on your cross section?
It would be right. It starts really where the subduction starts. So once it starts subducting, it would be right there. It would then go. I'm not sure where the temperature hits 350 degrees.
Well, no, that's all. That's all that I would have liked to have seen on this diagram.
Yeah.
Is on the left you show the locked, the transition, and the tremor zone according to Heinemann, which you say is held up pretty well, and I agree.
Yeah.
And on the right, you only show the tremor zone, the
Yeah.
ETS zone, and not the locked or transition zone, which another version could do that. Did we lose that for some reason?
Well, actually, I guess, I mean, kind of just looking at the slide, if it starts, once it starts subducting, and it goes not quite to the coast. So, I mean, if I was drawing it on the map, and I don't know how good that map is, and
No, on the cross section is where we
on the cross section, you see the blue is the water, so it would end.
Yeah.
So
this is another good example of a topic that could be an entire course, and probably is at the University of Washington or Oregon State or University of Oregon, because this is, you can imagine there's a lot of research going on to that. Can we go to your table very quickly?
Sure.
This is really quite remarkable. So we've got 5 different scientists talking about the periodicity of, you said it had to be something like a magnitude 8 or 9 in order to cause a tsunami, and it's an order of magnitude difference, or maybe even 2 orders of magnitude difference, in terms of the estimate. Obviously, this is of the critic, the $64,000 question is, how often between these major earthquakes, and with only one data point, it's very difficult to have any confidence. And you can imagine the insurance companies might be interested in this problem.
Absolutely.
So anyway, that's very good.
I don't think I went over it, but I think Goldfinger, who you probably know him, and you probably know that he's great, whatever, but he's saying a 10 to 15% chance of a magnitude 9 quake in the next 50 years, and he's basically a 37% chance of a magnitude 8 quake. And really, there's probably a little bit difference. I mean, it seems to move the whole plate, but the Explorer plate and the Gorda plate are kind of separating and destroying and deforming themselves. But there is some where, because of that Oregon situation, that sometimes it looks like maybe the north will move just by itself, or maybe the south will move just by itself. So then you obviously have a much lower magnitude quake.
Yeah. Okay, we better move on. Thank you for a very interesting topic.
Yeah, I'm Bochen Dom. So today it's my final project. So on January 7th, 2025, there was a pretty major earthquake in Dingri County, Rikaze city in Tibet. It had a magnitude of MI 6.8, and the epicenter was about 10 kilometers deep. Sadly, it caused 126 deaths and injured about 350 people. So while talking to Bob, he brought up how satellites can be used to monitor ground movement, which really caught my attention. So I decided to give it a try myself and explore INSA data processing. Yeah, the basic idea is get rid of image taken from space, specifically Sentinel-1 SAR data, which you can download from the place like Copernicus or the ASF portal to see how the ground moved. You need to choose data, at least 2 data scenes of the same area taken at different times, since Sentinel-1 passes by the same spot every 12 days. I chose images from January 1st and January 13th, 2025. You will also need a digital evaluation model, precise orbit data, and optionally some files can help with the processing. Okay. Well, there are some missing. Well, I used a tool called IIC to do all the processing. It generates something called interferograms and maps out how the ground might have shaped. Here's a quick rundown of the steps I followed. I will let you know. The first one is download. The next one is unpack, and the organize these. Extras boost overlaps, create steps, the baseline, and create average baseline crop, resemble split, merge swipes, and call register and generate interferograms, major interferograms, and filter, calculate coherence. The last two steps is unwrap, and the last one is geocode. So after running through this pipeline, I managed to generate a few useful products. This is the first one. So this one is a coherence map. This is a grace. This is the connected components. This one shows which parts of the image could be unwrapped properly. Each color is like a separate patch of the stable signal. Most of the thing ended in a single big patch, which means the unwrapping step worked pretty well. Yeah, calculate. Yeah, this one is a coherence map. This is a grayscale image showing how consistent the signal is between the two dates. Bright areas, which is white and light gray, means the surface didn't change much. It's a good signal. Dark areas means low signal, often due to snow or vegetation. Luckily, the main areas I was studying had decent coherence. So this one is unwrapped phase. This is a color-coded map showing how the radar phase changed, which hints movement toward or away from the satellite. Big shifts in color, like yellow to blue, might suggest the ground movement. And the last one is the light of sight, LOS displacement. This is a final deformation map. It shows up to 3 centimeters of motion, especially in the southern part of the state. To be honest, the result wasn't amazing. A big reason is that I had to lower the resolution to about 300 by 300 meters because my laptop just doesn't have enough power to handle higher precision. I really wanted to get more detailed results, but I had to make those process smoothly finish. That said, it still shows how powerful and convenient satellite data can be for studying surface deformation. Looking back, I do have a couple of suggestions if I were to do this again. First, I think geocoding should be done in the process to make the results easier to interpret. And second, I used a pretty small here. Ideally, you'd want more things to improve accuracy, even just these two images took those two images took about 100 to 200 GB of space, so I had to work within my limits. Anyway, despite all that, this was a super valuable experience for me. I got to walk through the whole INSA workflow and understand what it takes to process satellite read the data. It also gave me a better appreciation for how much computing power is needed for this kind of work. Yeah, that's all. The next slide is the reference. Yeah, I mainly use the code of the ISCE2, which is available for everyone. And thanks for our thanks for our Professor Bob and TA Clinton, and yeah, thanks for the textbook. Thanks for my classmate. Yeah. Yeah, and I think I just on slides. So I think my previous
Okay, do we have any questions?
yeah, my previous slides should be have the map created by GeoMap app.
So
Yeah.
did any questions from the class? That was an excellent effort to try and actually attack a problem. Oftentimes, the first time we go after something, there's problems. Now, did you make your PowerPoint using the Microsoft PowerPoint, or did you use some other software?
I use Microsoft PowerPoint, but I've got to save before I submit to Clint. So I think it's a problem. Can I just submit a new one? I think I'll change a little bit the.
Yeah, it's good to make sure that it is
yeah, that's my problem.
it shows up. Well, this is a class and you're learning. So number two, don't we have more powerful computers in the department that could do the processing more rapidly, better than your laptop? I mean,
unfortunately, I don't have access to use those computers too, and I also can't install any software and change the conda environment. It needs the what is that, the administrator to agree.
yes.
Yeah.
Well, we can do these things. Did you discuss this project with Yuji, our interferometry professor?
I took a seminar from Yuji last semester, so this is my idea from that. But this time I'm a new beginner. I just try this by myself.
Well, this is good to try it by yourself, but when you run into roadblocks, you should talk to somebody to help you, right? This is an important thing for all students to learn is, yes, be sure and try something and take it as far as you can. But when you reach a roadblock, reach out to other students and faculty to see if they have suggestions. So for example, if you wanted to use a more powerful computer that's set up to do interferometry, I think Yuji's on leave. She has a new baby. I think that's true. So but are you going to continue this work for your dissertation, or what are your plans for your dissertation?
My plan is to focus on the seismology with Josephine, our new stuff. Yeah.
Okay, good. All right. Well, we have one more presentation, and Brad, take it away.
All right. I see how you are, Clint. Save the worst for last. All right. So my name is Brad Forsyth. My research is entitled Mantle Plume Migration. It's a challenge to the fixed hotspot paradigm in plate tectonics. Basically, I'm going to talk about mantle plume migration using Hawaiian Emperor Seamount chain as the main case study. We'll look at some of the different types of data that help us figure out whether hotspots like under Hawaii are either fixed in place or if they move over time. This question ties directly into how we understand plate tectonics and mantle dynamics, so it's an important part of the bigger geologic picture. All right, so this project focuses on investigating the mobility of mantle plumes, specifically whether they remain fixed in place or migrate over geological timescales. This has major implications for how we understand plate tectonics, especially when interpreting hotspot trails like Hawaiian Emperor Seamount Chain. To evaluate plume behavior, I used three primary methods. Hotspot tracks, which show time progressive volcanic activity and give clues about relative motion. Paleomagnetic data, which helps reconstruct plate positioning and motions using magnetic signatures that are preserved in the volcanic rocks. And seismic tomography, which provides images of deep mantle structures that can reveal plume shapes, tilts, or bifurcations. All this leads to central research question of, are hotspots truly fixed or do they migrate over time? The following slides present the evidence and theories that help answer this question. Here I drew a map, just a general map showing the plate moving and creating a volcanic chain over that hotspot plume. So mantle plumes are thought to be deeply rooted in core mantle boundary and buoyant, creating hotspots when they reach the lithosphere. Hotspots show volcanic activity even away from plate boundaries and can be found in the middle of a tectonic plate like Yellowstone in Hawaii. According to the fixed hotspot hypothesis, plates drift over stationary plumes, producing a linear track of progressively older volcanoes, such as the Hawaiian Emperor Chain. These features are key tools in tracking tectonic plate motion over geologic time. As the plate moves over the hotspot, new volcanoes are formed and create what is known as tracks. These volcanoes increase with age further away from the hotspot and are no longer active. There are currently 6 active volcanoes directly over Hawaii hotspot, with the 6th active volcano just growing right off the coast. All right, so here I used GeoMap app to generate the location of the Hawaiian Emperor Seamount Chain. This map clearly highlights the infamous Hawaiian Emperor Bend, which is a major change in the direction of the Seamount Chain. While the Pacific Plate has undeniably moved over time, the critical question is whether plate motion alone accounts for this bend or if the hotspot itself has also migrated. At the southeastern end of the chain near the Big Island, we see another subtle change in direction, suggesting a new phase of activity. The region has produced larger volumes of magma and exhibiting various variations in geochemical composition as well. This raises important questions. Is this shift solely the result of continued plate movement, or could it indicate a changing or migrating mantle plume? Could the plume now be interacting with a different portion of the lithosphere or crust? Is the mantle plume being recharged by a new source of enriched material from deep within the earth? These observations support the idea that hotspots and mantle plumes are dynamic, and their interaction with moving plates is more complex than previously assumed. So again, in this map, you can see from the very beginning, 81 million years ago, of Detroit, all the way down to the bend where the Decajui is at roughly 47 megaannum. Abrupt change there, all the way down to the main Hawaiian Islands, modern day. But again, the new bend is creating right there at the new Hawaiian Islands. You can see it's getting larger, thicker, and going south again. So it took me a minute to realize, but you can see the first half, 81 to 47 megaannum, is the Emperor Chain, while 47 to modern day is Hawaiian Chain. Well, not modern day, but current day. All right, so the Hawaiian Emperor Bend represents a sharp 60-degree directional change in the hotspot track between the Hawaiian Islands and the Emperor Seamounts. There are over 129 volcanoes in this chain, stretching over 6,000 kilometers. The oldest volcano is about 81 million years old, and the bend is dated around 43 million. The youngest volcanoes are found around Hawaii, the Big Island, where Mauna Loa stands as the largest chilled volcano on Earth. By analyzing the chain, scientists have mapped the Pacific Plate's movement over the last 80 million years. However, models do not align the plate motion with the age distribution of volcanoes. Doing so would require a southward moving plume. This implies that both plate motion and hotspot plume migration were involved in shaping the chain's length, geometry, and volcanic age progression. If plate movement alone caused the bend, the chain would be about 800 kilometers shorter. The abruptness indicates deeper mantle forces at work. One theory proposes that rapid, coherent flow in the deep mantle pushed the edge of a lower mantle pile rapidly southward, tilting it. When this base motion stopped, the plume became vertical again, causing the bend. This start-stop motion strongly suggests we need better understanding of mantle dynamics, especially near the core mantle boundary. In the image I drew here, you can see as the tectonic plate moves, if we leave the hotspot stationary, the convection in the mantle will just continue to feed roughly in the same spot and just pop up new seamounts. Well, the seamounts are created later as the plate moves on and the water erodes it down. But you can see how the mantle plume itself just feeds in one specific place as the plate moves across it. Okay, so in this image I drew, basically took a couple of different ideas and threw it all together into one. In green, you'll see where tracing it back coincides. If we stick with just actual what we know and what we see and how the actual chain is, you can follow blue all the way back to Detroit, 81 mega annum. But if we use paleomagnetic data to reconstruct plate motion alone based on fixed mantle plumes, you can see in red that it doesn't line up with what actually is. So as volcanic rocks cool, magmatic minerals with them align with Earth's magnetic field at the time of formation. This allows paleomagnetism to serve as a geologic reorder of magnetic field direction. These paleomagnetic records are used to reconstruct apparent polar wander paths, which help geologists retrace past positions of tectonic plates. Obviously, we can't do that alone with just that, but other things can help and assist. If the mantle plume beneath Hawaii were stationary, paleomagnetic evidence indicates the volcano chain would follow a different track. It would have a less sharply bent and compared to what we actually see today. This discrepancy suggests that both plate motion and plume movement occurred, with paleomagnetism indicating a southward migration of the plume. Specifically, paleomagnetic and radiometric data indicate that the Hawaiian hotspot plume moved rapidly during the late Cretaceous to early Tertiary. If we were to generate a map based on only plate movement, you would see what's in red there in the map. Some studies even argue that the plume moved more than the plate itself, which adds complexity and certainly to current tectonic models. And I don't think I would believe that as much. It doesn't make sense for a plume to be moving more rapidly than a tectonic plate itself, but there are limitations, including potential remagnification of rocks and sparse paleomagnetic data across some parts of the chain. Ultimately, this evidence impacts computer models of mantle convection and underscores the need for a better understanding of Earth's internal dynamics, particularly how plumes and plates interact with the mantle. So recent seismic tomography has identified two distinct low-velocity mantle anomalies beneath Hawaii. I thought this was quite interesting theory here. This supports double plume theory proposed by Zhang in 2023. The original Hawaiian plume appears to be compositionally depleted and dying out, while a younger enriched Loa plume is rising and becoming dominant. Evidence suggests that this interaction between the two plumes has been ongoing since the formation of the Hawaiian Emperor Bend around 43 million years ago. Geodynamic modeling indicates that the southward deflection of the volcanic chain, the bend, could be the result of a plume-plume interaction, not just changes in the Pacific plate motion. Although the Lilla plume activity is most prominent in the last 5 million years, its influence may extend further back, potentially overlapping with a protruding the Hawaiian plume. This theory also raises the possibility of failed or suppressed hotspots that never reach the surface, leaving subtle geochemical or geophysical signatures. The enriched Loa plume could explain the increase in volcanic activity in the more recent part of the chain, particularly in Hawaii, the new bend around Hawaii. This double plume model emphasizes that the lower mantle is not static. It is highly dynamic and reorganizing, affecting hotspot formation and plate plume interactions. Overall, this model provides a more complex and realistic view of how mantle plumes behave over geologic time and could explain similar bends or anomalies in other hotspot tracks worldwide. So I drew these three images here to try and show the whole theory behind this plume-plume interaction. The first picture, you can see how the normal Hawaiian hotspot there just makes a single straight line as the tectonic plate moves in a single direction or in the direction with an emerging second hotspot. The second picture there shows as it gets larger and rises higher up towards the lithosphere, you see it starts pulling the older plume towards it, which then starts sidetracking the volcanic chain up top on the top of crust, even though the plate motion might be consistent or not changing. The third one there shows basically what's going on with Hawaii right now as a plume-plume interaction, as it has completely pulled it over off to the side and causing additional volcanism, larger amounts, and then also the abrupt southern change again, creating another bend. So studies show that while some hotspots are stationary, others clearly migrate. Paleomagnetic and geodynamic evidence point to complex behavior in Earth's deep interior. Interactions between plumes or sudden shifts like those seen in Hawaii imply a dynamic mantle. We still lack clear understanding of why some hotspots don't move. A better view of the core mantle boundary could unlock answers about plume origins and motion. And these are my references. Questions?
Looks like John's trying to ask a question. Is that right, John?
Nah, well, I kind of have one, but it's not really coherent. So, but
Oh, let's hear an incoherent question.
well, I mean, so the Big Bend in 43 million years ago, that couldn't have been like what's taking place now. It had to be something else, change in subduction starts or whatever.
It could be the same exact thing. That plume, like right now, if let's say that double the plume theory is right, or even failed hot spots in the past, it could have started and it abruptly just released a lot, and the two of them worked together and created that bend, and then that new one just died out, and it allowed it to go right back to its normal shift. But now all of a sudden, here we are, 47 million years later, it's come back again, and it's influencing it again, causing another bend right where the Hawaiian Islands are. But that's just another theory. Yeah.
So, Brad, can you bring that map up and let's chat about it a little bit?
Clint?
If you're tired of being a geologist at some point, you got a career as a graphic artist, that's for sure.
There we go. So what we see, so you've identified a very complex hypothesis of migrating plumes that is very difficult to test.
Yes.
But, so very simple-mindedly, if we wanted to interpret this trend as reflecting something with a fixed hotspot, what could possibly explain that?
So with a fixed hotspot, you still have tectonic motion going around. You have subduction on one end, you have you know, movement trenches on other ends. So they don't just move in a straight line, like they can rotate as that plate moves, which that can also cause more abrupt
Well, you're
push
getting very
pull.
complicated very quickly. Is there a simple explanation?
Is if it's a fixed hotspot,
Yes.
if it's a fixed hotspot, it would still be mantle convection, something going on between the
No. Just the plate is moving. So this is the world's best hotspot chain. I mean, everything. The question is, what's in second place? This is definitely,
So
the
if it's
gold
just a fixed
standard.
hotspot, then the plate is just simply changing its direction as it moves.
That's right. So, and when did the plate change its direction?
47 million years ago.
Or whatever about that time. There's been more recent dating that argues that the bend is at closer to 50
Yeah,
or 52,
44, 55. Yeah, I've seen a couple of
it's
them.
around then. So let's assume that the plate changed direction about that time. What was the direction before and what is the direction now?
Yeah, so it seems like it was more northwest before, and then it abruptly moved south. And now it's starting
It's
to
not
go.
moving south. You're right on the first
So the
part.
plate's moving north, but the plume is supposedly moving south abruptly.
The plume, we're going to keep the plume fixed for now.
Okay.
I do
So then it started
appreciate.
moving west.
So it started moving more west. Now, what could do that? What could cause the plate to suddenly make a hard left turn?
Push pull of plate tectonics, subduction.
So what is the most important control on plate motion?
Push and pull, convection.
What causes 90%? It's a midterm question. What
subduction?
causes? Right. So in order to have that change, something had to change in
Subduction rate.
Subduction zones.
Yeah.
So is there a subduction zone like Marianas or something like that that's
absolutely.
47 million years old?
Well, more to the point, we have strong evidence that subduction began beneath the Izubonin Mariana Arc, which is that trench that goes, whoops, you slipped us away there. Slippery. Can you put it back?
The
Izubonin Mariana Arc, everybody can see Japan. The Izubonin Mariana Arc goes directly south from Japan. And that subduction zone started about 50 million years ago. So you have
west change.
Yeah, and the Aleutians and the Kuriles up in the north, they're still subducting, but the net force on the Pacific plate is a combination of subduction in the west and north and the south. So it is actually a quite confident result that the beginning of subduction, especially in the Western Pacific with Izubonin Mariana, pulled the Pacific plate in that direction at about that time.
Which suggests that with a fixed plume, as of right now, all of a sudden that west Pacific plate subduction is slowing down dramatically and allowing more northern movement. But still the question arises, why is the composition of the volcanic activity being re-enriched and coming out at larger amounts?
Well, this is kind of the way we do science. We look for first order explanations, and then we have a model. We have a conceptual model of what's happening. But as we have said, I think several times in this class, all models are wrong. Some models are useful. And by saying that the only thing that's going on is the Pacific plate was moving north-northwest prior to 50 million years ago and is now moving west-northwest, that's a model. And it's wrong, but it's useful because in addition, it doesn't address the question of is the Hawaiian plume moving at all, because the Hawaiian plume could still move quite a bit You know, the scale of the big island of Hawaii, those of you that have been there, you know, it'll take you all day to drive around it. And there's two, the Loa trend and the Kea trend, which you discussed. Those are sort of at the scale of that island. But I think we have to leave. Clint's got another thing. You guys have done an excellent job of looking at different interesting tectonic problems and I hope you've learned something useful in this class. And those of you that are going to take the final exam, good luck.
Thank you.
And we'll
Hey,
see
Brad, did the composition change when it changed direction too? Is that what you're saying? Okay.
Yes. Yeah, it shows that it's
Okay.
depleted in enrichment, but then it's re-enriched.
I would like to see that data. This is not a petrology class, but
Yeah.
For those who are graduating, good luck in your careers and thank you for your help in the meantime. So
yeah, hopefully we'll see y'all later.